Alright, so today we are covering pairs of roots and potentially something else too, but our first topic for this video is pairs of roots. And so if we recall our fourth axiom, which was that the square bracket between beta and alpha, which I believe was 2 of the form of beta and alpha over alpha and alpha, is an integer. This limits the possible angles between pairs of roots. If you recall that the angle theta between vectors alpha and beta in our Euclidean space is given by that the magnitude of alpha times the magnitude of beta times cosine theta is equal to our form alpha beta. Therefore, we have that the angle bracket of beta and alpha is equal to 2 times the form of beta on alpha over the bracket of alpha with itself, which is 2 times the size of beta over the size of alpha times cosine theta. And we have that the bracket of alpha and beta times angle bracket of beta and alpha is just 4 times the square cosine of theta. The last formula here is a non-negative integer, but 0 is the cosine squared of theta is between 0 and 1, and the sine of alpha angle bracket beta is equal to the sine of beta bracketed angle bracket alpha. So we have only the following possibilities. When alpha is not just a scaled version of beta, and we're going to assume without loss of generality that the size of beta is greater than or equal to the size of alpha. Now I need to copy out a table, so that's going to be a new exciting adventure for me. First column, we have the bracket of alpha on beta. In the second column, we have the bracket of beta on alpha. We have the angle it generates, and we have the size of beta squared over the size of alpha squared. And we just have, I'm just going to copy them down like this. This is not a good solution for this problem, but what are you gonna do about it, you know? So we can see that this one is always going to be 1 or -1 or 0. You know, lots of options to choose from. The angle of each line is getting worse. I hope this isn't the thumbnail of the video. And this is going to be some multiple of this from 1 to 3, which gives this as pi over 2, pi over 3, 2 pi over 3, pi over 4, 3 pi over 4, pi over 6, and 5 pi over 6. This is an indeterminate form, and then we just have the ratio here, which you can get from the values on the left. And we see all of these in our diagrams. And this comes with a lemma. Let alpha and beta be non-proportionate roots. Proportionate roots. If the angle between alpha and beta is acute, then alpha minus beta is a root. If the angle between alpha and beta is not, then alpha plus beta is a root. I'm scrolling down more aggressively than usual to hide my horrible diagram. We only need to prove the first. By the fact that by substituting beta for negative beta, now since alpha beta bracket is greater than 0 if and only if the angle bracket of alpha and beta is, we see that either alpha and beta or bracket of beta and alpha is 1. And we can just see this from my horrible diagram here. If it's the bracket of alpha on beta, then sigma of beta on alpha, the beta reflection of alpha, is alpha minus beta, which is a root by axiom 3. And if the angle bracket of beta and alpha is 1, then by that logic beta minus alpha is in theta, and so will be its negative alpha minus beta. Okay, so let's have a quick discussion of this afterwards. Consider non-proportional roots alpha and beta. Look at roots of beta plus an integer times alpha, which as we recall is the alpha string through beta. We're going to pick R and Q in zeta positive, the largest integers such that beta minus R alpha and beta plus Q alpha are roots. If some beta plus I alpha is not a root for, like if we want to say that there's a gap in this string, find p less than s in this interval such that beta plus p alpha is a root, and the next one, beta plus p plus 1 alpha, is not a root. And then with the same for s in the other direction. S alpha is a root, but s is kind of our bottom here. Then we have both that alpha bracketed with beta plus p alpha is 0, and alpha plus alpha with beta plus s alpha is non-positive, which is a contradiction, as p is assumed to be less than s, and the bracket of alpha with itself is 0. Thus, the alpha string through beta is unbroken. From minus r to plus q. Now, as sigma alpha just adds a multiple, could be a negative multiple, of alpha to any two roots, this just preserves this. This just reverses the string. Remaining invariant. Remaining invariant. With sigma alpha of b plus q alpha being equal to beta minus r alpha. The left side is then beta minus the bracket of beta alpha minus q alpha. So finally, r minus q is equal to beta and alpha. Thus, root strings are at most 4 long. And that's the end of that chapter. Up next, we will be looking at simple roots and the weyl group. Our first topic in this being bases and weyl chambers. So, a subset delta of phi is called a base if, first off, delta is a basis of E, and secondly, each root beta can be written as the sum of elements from this basis with integral Ka all of the same sign or zero. Sign or zero. And the roots in delta are called simple. From I, we see that the cardinality of delta is the dimension, and that the expression of beta in part 2 is unique. Thus, we can define the height of a root relative to delta as the height of beta is the sum of its scaling factors from above. If all k alpha are positive or zero, we call beta positive, and likewise negative if they're all negative. Or say that beta is greater than 0. The collections of positive and negative roots and negative roots are written as phi positive and phi negative. You see that if alpha and beta are positive, alpha plus beta is positive, assuming it's a root. We see that delta defines a partial order on E. we define that beta is less than alpha if alpha minus beta is a sum of positive roots. Or alternatively, simple roots. Now we need existence. We still need existence of bases. In the drawn examples, alpha and beta form bases. If you want to go back to the last video, and notice that it's always obtuse. The form of alpha and beta being negative, non-positive. This motivates the following lemma. If delta is a base of phi, then the angle between distinct roots in delta is obtuse, and alpha minus beta then is not a root. We have the second part automatically from before. Since we have alpha is not equal to positive or negative beta, then A alpha minus A beta would be a root. Otherwise, okay, I'm just gonna write this out verbatim because I don't understand their wording here. Otherwise, the bracket between beta would be positive. Since alpha is cannot be obviously positive from negative beta, this would make alpha minus beta a root, violating condition 2. So I guess this is proof by contradiction, assuming that the bracket of alpha and beta is positive. Now, our goal is to prove a theorem which every root system has a base we will see that for each vector gamma in our Euclidean space, define the positive root function of gamma to be, no, it's going to be the set of alpha in phi such that whose inner product, whose form with gamma is going to be positive. This is going to be the set of roots on the positive side of the hyperplane of gamma. And we know that finitely many hyperplanes as a union cannot exhaust E. So we call a vector gamma and E regular if gamma is in E and not in any of the hyperplanes defined by the roots, and singular otherwise. When gamma is regular, we have our root system being the positive roots of gamma plus the negative roots of gamma, since we know that none of them lie on the hyperplane defined by gamma. Now we're going to call an alpha in phi positive of gamma decomposable if alpha is equal to beta 1 plus beta 2 for some beta I in gamma positive of y and indecomposable otherwise. Thus, we have an equivalent to our theorem, which we call theorem prime. So we have a regular vector in E. Then the set gamma y of indecomposable roots and gamma positive y, phi positive of gamma, is a base of phi, and we get every possible base from this. Let's look at the proof. We need a new page. Okay, first part. Each root in gamma positive of y, phi positive of gamma, why do I always say that, is a non-negative z-linear combination of elements in delta of gamma. Otherwise, we have that some alpha in phi positive gamma cannot be written this way. choose alpha to minimize gamma, bracket of gamma with alpha. As alpha, it cannot be in delta gamma. We have alpha is the sum of beta 1 plus beta 2 for each of these beta I being in phi positive of gamma, so that the form of gamma and alpha is the form of gamma and beta 1 plus the form of gamma and beta 2, but each is positive of these terms on the right is positive. So each beta I must be non-negative z-linear combos, z-linear combinations of delta of gamma. So A is, try to draw the contradiction symbol. There, that's pretty good. 2. If alpha and beta are in delta of gamma, then we want to prove here, then the form of alpha and beta is non-negative, is non-positive unless alpha just straight up is beta. Otherwise, alpha minus beta is a root. Since beta is clearly not negative alpha, so alpha minus beta or beta minus alpha is in gamma positive, phi positive of gamma. In the first case, alpha is beta plus alpha minus beta, so alpha is decomposable. And similarly, swapping alpha and beta in the second case. And that's a contradiction. Part 3 states that delta of gamma is linearly independent. Suppose that the sum of our alpha is 0 for alpha in our delta of gamma and R alpha being real. Splitting these indices by the sign of R alpha we get the sum of S alpha alpha is equal to the sum of T beta beta. With each S alpha and T beta being positive, and the set of alpha and the set of betas are disjoint. I'm going to call epsilon equal to the S alpha of alphas. Then the form of epsilon with itself is the sum of S alpha T beta times the form of alpha and beta, which is going to be non-positive. So epsilon is 0, so all S alpha and T beta are 0. Condition. Step 4, that delta gamma is a base of our root system. Since we've seen that phi is phi positive gamma and phi negative gamma, their union, we have condition 2 by step 1. We also have that delta gamma spans E. So by 3 we have condition 1. Step 5, that each base delta of gamma has the form of delta gamma for some regular gamma in E. So given the basis delta, we're going to select a vector gamma such that the form of gamma and alpha is positive. It's an acute angle with every element in the basis. Given that the intersection of positive open half spaces is non-void under the conditions we have. From axiom 2 of the bases, we have that gamma is regular, and phi of positive is contained within phi of positive of gamma, and phi negative, which is equal to negative phi positive, is contained within negative phi positive of gamma. So we have So we have actually equality for each instance. Thus, delta consists of indecomposable elements. So delta lies within delta gamma, as the cardinality of delta is equal to the cardinality of delta gamma equals L, delta equals delta gamma, and we are done. I just want to check something real quick. Okay, yeah, we got just enough time, I think, to finish off this chapter, and then we'll be done and in a more reasonable place for next time. So now we note that the hyperplanes P alpha, for obviously alpha being root, partition the Euclidean space into finitely many regions with the connected components of E minus the union of these hyperplanes being called weyl chambers of E. Each regular gamma in E belongs to a unique weyl chamber, which we're going to call C of gamma. Saying that C of gamma is equal to C of gamma prime means that gamma and gamma prime lie on the same side of each hyperplane. Each hyperplane P alpha, so that phi positive of gamma is equal to phi positive of gamma prime. So the bases they generate are the same. Thus, we have a bijection between bases and weyl chambers. I'm going to write that the chamber of a basis is equal to the chamber of gamma if that basis is generated by that vector. And we call this the fundamental weyl chamber relative to our basis delta. The chamber of delta is the open convex set. Convex set of all gamma in E such that gamma, the product of gamma and alpha is positive for all alpha in our basis. Now, the weyl group, they have a diagram of the weyl bases. It's just like you have, like, example, if you have, this is your root system, they're just going to be like this, and one of these is going to be the fundamental weyl chamber of your basis, depending on what you choose. The weyl group sends one weyl chamber onto another, with sigma of the chamber of gamma being the chamber of sigma of gamma. For sigma be an action of the weyl group and gamma being regular. We also see that the weyl group permutes bases. With gamma sending a basis to another basis, another base, I should call it, not a basis, sigma of delta. And these two actions of the weyl group are compatible with the previous correspondence. The correspondence of weyl chambers and bases with noting that we have sigma of gamma of delta is delta of sigma of gamma, as sigma of gamma and sigma of alpha is equal to gamma and alpha, their forms. Alright, and we'll call it there. We're carrying on with our root structure math. Next time, we're getting right up to our limit here. But I saw it briefly mentioned Bourbaki talking about this, Bourbaki and Sayre, so I'm going to have to double check on that because I didn't see anything. Maybe it's in a different book than what I'm using. I don't know. I'll work that out later. Thanks for watching.